Morning, guys. Excuse me, 5.2 we're on to. 5.2a. We're going to have a B and we're going to have a C. And that means we're probably going to be having a test sometime next week, maybe Thursday, Friday-ish, okay? But bottom line, what we've been doing here in Chapter 5 is we've been summing the area of rectangles formed between the x-axis and f of x on some interval from a to b, which means, bottom line, we just have a little graph. Here's my f of x, doesn't matter. Here's my b, here's my a. We've just been finding a whole bunch of rectangles in here, right? We've been adding all those rectangles up to estimate the area that is between the function and the x-axis between a and b. And we do know, as the number of rectangles, the more rectangles I put between a and b, the more accurate my approximation gets, okay? And it's been kind of a painful endeavor, I get it. And there's, as you continue in math, things get easier and easier as they go. And bottom line, we're looking at the area of each rectangle is some f of c times delta x, where these are three very special specific values that we need, okay? Now remember, f of c sub k, that's what we're going with that, right? Which, what the heck is delta x sub k? That's right. It's the width of each rectangle. It's the width of the rectangle. And remember, the widths do not have to be the exact same. However, for the ease of our calculation, we're making them all the same. And the way we're finding this delta x sub k, we're always taking b minus a divided by n. That's how we found it every time. Then we run into this c sub k value. What the heck is that? Hey, this c, we've been working with this c sub k value, and there's a reason why I've been beating the tar out of the c sub k. Well, it's simply an x value. That's all it is. It's an x value. It's a happy x value, okay? And it's an x value that's used to find the height. It's used to find the height of the rectangle, okay? And that c sub k, sometimes we use the left side, sometimes we use the right side, sometimes we use the midpoint between there. But as we were cruising along, we've been doing the right ram for a while, and that c sub k, every time we said our c sub k, we said, hey, that was our a value plus our delta x times k, and we found all these heights because then k equaled 1, then 2, then 3, then 4, all the way down to the last one we had there, right? And that found all of our different rectangles. Remember, k is just a counter. C sub 3 is, oh, that's the right endpoint of my third rectangle. Big deal, okay? And then we found f of c sub k. What the heck was that? That was the actual height of the rectangle. It wasn't the height of the rectangle until we plugged c sub k into the function. Okay? And then we cruised along here and we figured out the area on a to b using n rectangles. Okay? Now remember, we did this a long time. N is a finite number. And I'm saying n is a finite number here. And there's a reason why I'm saying that, and I'm going to point that out. And all we did was we took all these areas, our n was a finite number, where we took our heights times our width, we summed them all up, and when n was a finite number, this was an approximation. This was an approximation of the area when n was finite. That's why the little doohickey is there, and was an approximation. Okay? Well, then we moved on and we kept cruising. Now we said, ooh, n's approaching infinity. And as we got an infinite number of rectangles, ooh, that was a limit, okay? Well, notice what changed in our area equation. As soon as n went to infinity, that gave us the exact area. It was no longer an approximation. And as soon as we took this limit, okay, this is called the limit of a Riemann sum. I spell that Riemann. I spell it wrong every time. I-E-M-A-N-N. The limit of a Riemann sum, as soon as I got into this, well, that's specially known as the definite integral of f of x on the interval from a to b. And when we look at this, we're in this particular notation, because it's all symbolic, it's like, oh, well, we can kind of see what f of x is a little bit. We don't know what a and b is, but a definite integral is noted as the integral from a to b of f of x dx. Okay? Well, what is this? Well, here's my widths. Here's my height. There's my width, or there's my heights, excuse me. F of x, I plug them in. Delta x of k, differential notation. That's my width. I'm still taking heights times width. It's just a shorter notation. Okay, we're building along, and when I'm taking the limit of a Riemann sum, it's kind of weird. Some mathematicians someday, I don't know why they did, I have no idea, curious why, but when I'm taking the limit of a sum turned into that notation. And a little stretched out s kind of means sum, okay? And it's called a definite integral, and it's a definite integral. I'm just going to get ahead of it a little bit here, because there are limits of integration on it. Because there are things called indefinite integrals, and indefinite integrals do not have limits of integration on it, okay? So a definite integral will always output a value in the end, not a function. It's going to output a value, okay? And what's going to happen is you're going to be given limits of a Riemann sum, and you're going to be asked to write them as a definite integral on the AP exam. Promise you it's going to happen. Might be multiple choice, might get lucky and it won't be multiple choice, because it's actually a very easy task to do. Okay? Well, if I kind of look at some notes that we've done here, problems we did in 1A, and I'm just going to do these first two. One of them was f of x equals 9 minus x squared on the interval from 1 to 3. And we went through this painful anguish, and we knew, yep, it had a y-intercept up here at 9, had an x-intercept. It was half of a parabola. We were finding the area from 1, 2 to 3. And what we did was we broke that little bugger into a bunch of rectangles. We found that area. But in the end, we're saying, hey, that region, written as a definite integral, is going to be the integral from a to b of 9 minus x squared dx. Okay? So what am I saying? You mean you are wasting our time entering a whole bunch of stuff into a calculator when there's even a shorter way to do it? Yes and no. Fire up your calculators here, because now, when we're coming in, okay, we spent a lot of time taking all this, writing it like that, so we could type that cumbersome thing into our calculator. But it's important that we went through all that work, and we're going to continue that work today yet. But it's important that you know the shorthand version to type these in. Okay? And I got to fire up my calculator quick. Sorry, I'll be back in a second. Okay? So the goal of today right now, this is part of the goal. is we have yet another new notation for a sum. So I'm going to show you how to enter that into your calculator if you do not know how to already do it. Some people do. But what I'm going to have to do is I'm going to have to make a calculator page. All I had to do is actually hit, okay, on the 1. I forgot to hit, so I need a calculator, 1. Now, this function, this integral notation, that's stretched out S, I can find in my template here, and there's 2 of them. I have that one, or I have the other one, okay? And I can use that one. It's not working for me. Or I'm going to come back, or I can say menu, add a calculator. Come on. I'll try it one more time. I got that one, or this one. Okay? Oh, crumb. I didn't want to do that. So if I pick this off, this is a definite integral because you see this one has the little boxes. I don't have to put anything on there. But when I type this in, if my A value is 1 and I hit tab, it takes me up for my B value of 3 and I hit tab. I don't need to worry about parentheses. My calculator is very intuitive and it puts them in when it needs it. So I'm going to say 9 minus x squared. And then I have to tab to the outside, and I have to basically tell the calculator what variable I'm integrating with respect to. We're only going to have one variable in that function, and it's your independent variable, in this case is x, okay? And then all I got to do is hit enter, shazam, it's 28/3. Well, we found that out, I think yesterday or the day before, okay? And then we moved on to another one. We had number 2, we had f of x equals x squared plus 4, and we had to find that area from -1 to 3. Well, if we were looking people here, we kind of graphed it, and we said -1, 0, 1, 2, 3. Oh, that's 2, that's 3, and that's 1. And we found this area right here. Well, if I express that area as a definite integral, okay, it is the integral from -1 from A to B of f of x dx of my independent variable. So we found that area yesterday as well. So let's come back here, and I'm just going to show you another way to hit this. You can say menu if you don't want to use your template. Integral is a calculus. It's a number 4, and it's a number 3. It's an integral, and it gives me those in there. So I'm going to put my A value in, which is technically deemed my lower limit, tab, upper limit, which is my B value, tab. I'm going to type in my function, x squared plus 4. It intuitively tells me when it needs parentheses in my independent variable x, and I'm going to hit enter, and I get 76/3. Well, isn't that nice? Thank you for wasting all our time with entering them in with all these limits of the sum and in the summation. There was a point to all that. Please do not get angry, okay? There's a point to it. Now, then I'm going to come to the next one here, and we did have one more 5.1b worksheet. We came through all this, okay? And, excuse me, we worked through all this, and we could have graphed it. I'm not going to graph it, but we said delta x sub k, hey, that was b minus a over, because this was n was infinity, so this is a definite integral. So we know our definite integral is going to be hopefully from 1 to 4 of our f of x, which is 16 minus x squared dx. Okay, so this is how we write the definite integral straight from function form. Okay, well, we had to find the area underneath there. Well, what did we have to do? And we came through and we said that's 3 over n, and this c sub k, I think I drilled this c sub k pretty hard, where it's a plus delta x times k. And we wrote all that out, and then we went to the actual area limit. We said, oh, now our area, when it was an infinite number of rectangles, equaled the limit as n approaches infinity of the sum from k equals 1 to n of, and we plugged them in, and we said f of, actually I never even put that parenthesis there. And we said f of 1 plus 3 over n times k times 3 over n, right? And then you defined your function in the calculator, and we came through, and you hit enter, and it gave you the area. But I kept trying to beat it like a dead horse, and I said, hey, we're not going to see it like this on the AP test. How you're going to see it is like this, as a sum from k equals 1 to n of, we had 16 minus 1 plus 3 over n times k, quantity squared, times 3 over n. Okay? Well, the reason we went through that is because on the AP test, you are going to run into problems like this. And even if I had the graph up here, you're going to run into problems just like this. Okay? And it's going to say, your directions are going to say, express as a definite integral. What? Yeah, it's going to say express as a definite integral. And what's going to happen is all of this stuff on the top, you're not going to know any of it. They're not going to give you the blue form like I did, because that doesn't tell you anything about the function. And all they're going to do is they're going to give you this, and they're going to say, express the following limit, or express the following as a definite integral. And now it's to the point to where we worked with it a couple days, and we're going to identify, first and foremost, this means that. And then A and B are hiding in there, and of course, you know, A is right there, so you're going to say from 1 to 3. Oh, no, you're not. You're going to say from 1 to 4, not 3, because if my width is 3, and what do you mean the width is 3? Well, remember that 3, I know B minus A is going to equal 3, and it's all mental math. And if I know B minus, if I know A is 1 to equal 3, oh, B has to equal 4, so it's 3 units away from 1, so that's going to be 4. And then hopefully we're looking in here, and we can say, well, what is this? Well, I see my C sub k here. There it is, there's my C sub k. And I'm coming back and I'm saying, hey, what the heck is C sub k? And I come all the way back to the beginning, C sub k, hey, that's just an x value. So as I'm coming through, I'm looking at my C sub k, I'm like, ooh, that's just an x. So what I can do is I can say, oh, my function is going to be 16 minus x squared dx, and that's how I express it as a definite integral. It's not the only way to express it as a definite integral. That's the comfortable way you have right now to do it, okay? And we're going to build on that today, and then you type that in, and when we type that in, I'm not going to do it, the area was 27, okay? It's a key portion of the AP test that you know how to use your technology appropriately and quickly to do some of our calculus functions, okay? So then we're going to move on to the next one. And if I looked at this one, I can graph it if I want, but if I went through and I set this up like we did, okay, well, what the heck is delta x sub k? Well, we want the area underneath the curve. We are finding definite integrals and Riemann sums. We are finding exact area, okay? So we want to know delta x is 3 minus 0 over n. So that's going to be my width is 3 over n. Hey, what's my C sub k? Well, it's A plus delta x times k. And hey, really, we can write that as just 3 over nk, right? So when we plugged it in, we said originally, okay, the area equals, we took the limit as n goes to infinity of our sum from k equals 1 to n, and we did the shorthand version. We plugged in f of, and when you plug that in, because I watched everybody's homework yesterday, you said f of c sub k, that's 3 over n k times 3 over n, right? And that's what you plugged into it. And in the end, we need to identify this as our calculus version, the limit as n approaches infinity of the sum from k equals 1 to n of 8, right, plus, it's all under the square root, sorry, 8 plus 3 over nk times 3 over n. Okay? And you're going to run into this, and they're going to say, write this as a definite integral. Okay? Now, hopefully, I glossed over this a little bit fast. Okay? I did something I really didn't want to do, so let me throw my screen shade up here again. Before we even went, what I really wanted to do is say, oh, well, with what you learned today, hopefully, and it was a glossing over, it was really quick, but hopefully you understand this as a definite integral is going to be the integral from a to b of my function, which is the square root of 8 plus x times my width dx, right? That's my definite integral, okay? So what we did is we're coming down here and we wrote that out. So what I'd like to do is I would like you to translate this from what we had when we typed it in. This is the version the AP is going to give us. And I kind of did this a little backwards, but if you're honest with me, and I know you guys are all going to be honest with me now, I hope, we're going to take this and I want you to express this as a Riemann sum. And if you're being honest with me, I'm kind of thinking you're going to say this equals the integral, right, from 8, my width is 3, so 9, 10, 11, from 8 to 11, of the square root of x dx, right? Hopefully that's what you're saying, because that's, right, a plus delta x times k. So what the heck's going on here? What did we screw up? Something ain't right. That's all I know. Something ain't right. Now I got to get rid of this stupid screen shade. Come on, where are you, screen shade? I want to get rid of this. Well, hey, something's not right here because these are two different integrals, and there ain't no way they're going to be the same. So what's wrong? I don't know. Let's go check it out. So if I came here and I did a menu for, I like my hotkeys. I'll do a menu 43 for an integral. And if I typed in the first one, I am looking for the area from a to b of the square root of 8 plus x. And then I'm going to tab out and tab out. And my independent variable is x. And I'm going to hit enter. No, I didn't want to hit enter there. I'm going to come up. I'm in exact mode. So I'm going to go approximate. I didn't hit approximate. So I didn't hit control, enter. So I get about that. Well, what is the other one equal? Well, let's give it a menu 43, I think I said. And let's go from 8 tab to 11 of my square root of x dx. Really don't know how these things could possibly be the same. They look way different. And when I hit enter, I'm like, well, isn't that interesting? How can they be the same? They sure look different. Well, let me show you why they're the same. So if I actually, and I want to make some room here, and if I actually came back here and I took this and I graphed it, okay? If I graphed that, let me move this over. This stuff over. So if I graph the first one right here, what's going to happen is, if we're graphing by our wonderful transformations, right? Well, this means actually it's the same as x plus 8. So if I put negative 8 in there, I'm going to get a 0. And if I put, oh, how do I want to make this right? If I put a negative 4 in there, I'm going to get 1, 2 out, right? So I'm going to be up here about that. And it's actually going to kind of, I'm making it a little too technical. I'm not even going to get that technical. What's going to happen is my graph is going to go there, and I want my area from 0 to 1, 2, 3. And it's this area right here, isn't it? Well, this bottom one, this pink one, this has given me another one. But now notice where my starting point is. I'm at 0. And I just don't have enough room. I wrote too big at the beginning. I don't want to do that either. All right. So if I did this one, that one goes there, right? And what happens is now I'm down here from 8, 9, 10, 11. So now I'm really kind of finding that area. And because my scale is off so bad, all it is it's a horizontal shift. It's a transformation. Okay? So this is going to allow me to write my integral in numerous different ways. And actually, I'm going to pause, and I'm going to show you on the calculator better, I think. So hold on. Well, hopefully this makes sense, because the blue one's my first one right here. Okay, and we're finding the area from 0 to 1, 2, 3. We're finding this area right here on the blue one. And then when we're going on the red one, we're finding this area down here. And we found from 1, 2, 3, 4, 5, 6, 7, 8. We found from 8, 9, 10, 11, from 8 to 11. And what do you see? If you took that red one, if you took that point with the area converged on it and you shifted it, pulled it all the way back so it was the same, or you push the blue one forward, you hopefully can see that is the exact same area. So what comes up here is the dilemma, and I'm going to say kind of a dilemma, of how the heck am I supposed to write these integrals? And the answer is it really doesn't matter, okay? I can start any definite integral that I want. I can start them all at 0. What the heck are you talking about, Kruger? Well, here's what I'm talking about. So if I went through to write this the way we have the previous couple days, I'm going to take 3 minus negative 2 over n, right? So I'm getting 5 over n. Hopefully I'm getting 5 over n as long as I'm on my right example. Which means my c sub k is negative 2 plus delta x times k. Well, how did we go through all this business? Well, what's it going to look like? Hopefully we can see that this is going to be my integral from negative 2 to 3, okay, of 4 to the x dx. Okay, integral from a to b of the function times the independent variable, basically, derivative of the independent variable. And when we did this before, we were taking the limit as n approaches infinity of the sum from k equals 1 to n, right? And then what we're doing is we took in here and we said 4, and we plugged this in for our negative 2 plus 5 over n times k, times our width of 5 over n, right, as a definite integral. Well, it totally depends, okay? Now, when I'm looking, if I actually have something added directly to my delta x, as I do right here, I have something added directly to my delta x, that's just fine. I can look at that number that's added to my delta x as my a value, but I do not have to, okay? There's 2 ways to go here. Which way are we supposed to go? It really doesn't matter, but you have to be able to see equivalence, okay? And what I can do is if I came back here, the way you want to do it is you're going to say the integral. Well, there's my a, okay, negative 2. My width is 5, so I got to go 5 units away from negative 2. So 5 Negative 2 plus 5 gives me 3, so I can get that. Okay, I'm going to erase that 5. Oh, shoot. Dang it. This irritates me. Negative 2 to 5. My function, if this is my c sub k, my function is 4x dx, right? But what if I wanted to start my integral at 0 using a horizontal transformation? This may be, it doesn't have to be, it may be one of your choices. But the other one is let's come back here and let's say, okay, well, what if I start at 0? And what I'm saying is, if I start at 0, notice, where is it? Where is it? Not that one. Where is it? Not that one. I got it right here. Yeah, it was there. Notice, if I start at 0, whenever it's at 0 there, what is my c sub k? My c sub k is just delta x times k. Well, what if I do that? Well, if I did do that, here is my c sub k. And if that's my c sub k, just understand this is equal to the integral. Well, c sub k, there's nothing. If it's just my c sub k, my lower limit's got to be 0. My width is 5, so I'm going 0 to 5. The only thing that changes is now, that's my only x value, so I'm going to have 4 raised to the negative 2 plus x dx. And it's just a horizontal transformation encompassing the exact same area. And if you plug both of these, which you want to, okay, you plug these into your calculator, it's really important that you do this. And if you're just watching, going through the motions, not a good idea. But 43, if I grab my integral, I want to be able to make sure that you can type all these in, because we would be the integral, and it doesn't matter which one you type in, negative 2 to 3, if you did the first one, of 4 to the power of x dx, control enter, I get that sum. Okay, that's my area. If I went the other way with a menu 43, crumb, what'd I do? I don't know what I did. If I went a menu 4, 3, and I grabbed another one, and I went from 0 to 5, however, now my exponent is 4 raised to the negative 2 plus x, tab over to my dx. Now, hey, it's the exact same area. It's just dependent. As long as my width is the same and it's a horizontal transformation, I can make this work in any way, shape, or form that I wish. Okay? And so when we come to here, the last thing I want to do is, I really don't like the way the book has some things laid out, and your book does things stupidly. They say express the Riemann sum as a definite integral. Okay? And, well, they're really dumb, because here's their c sub k, so you can totally see the function here. If I went as a definite integral, well, I know a and b, they're not hidden on me anywhere. It's negative 4 to 2. Yeah, there's my c sub k. Those are just the x's as far as the book is concerned. So it's 3x squared minus 5x dx. That would be the definite integral. And when you plug that in, you will never ever see this notation. And I don't know if the newest levels of editions of this book do that, but you're not going to see that notation ever on the AP test. Okay, you're never going to see it that way. You're going to see it that way in your homework in the book, but when you see it on the AP test, here it is. Well, now we just switch gears. Express as a definite integral. Well, it's a little harder now. They didn't give you the function. I got to look in and find the function. But notice I have two options. I have actually an infinite number of options to write it. Two are very easy, because you see how there is, no pun intended, there's a constant added to my delta x. And whenever that happens, I have two quick options, okay? Option number one is how I default, because it's kind of the way I've been teaching you the whole time. I can default this and say, oh, this is going to equal the integral. Well, there's a. My width is 2, so I got to go 2 above a, so that's got to be 1 to 3, right? And what's my function going to be? Well, if this is my c sub k version in here, it's going to be 3x squared dx, okay? And hopefully if you type that into your calculator, when you do, I'm not going to do it, you're going to get 26, okay? Or maybe you don't want to see it that way. Some people are like this. Some people are like, I like to start all my integrals at 0. Well, you can if you wish, if you have a constant added to your delta x, okay? Because whenever that happens, I can say, hey, here's my c sub k now. It's not the whole set of parentheses. And if that's the case, there's nothing added to my delta x there. So I'm starting at 0. My width is 2, so I'm going to go to 2. Now, what's my function? My function is going to be 3 times 1 plus x, quantity squared, dx. Okay? Type that into my calculator. What am I going to get? 26. So practice it. Next one, I'm going to come along. Hey, there's a constant added to my delta x. I got options. Well, which option do you want me to use on the test? It doesn't matter, because it is very possible, guys, if they asked you to write this as a definite integral, they may have both of these actually in the answer and say both A and B. It may be one or the other. You don't know. They're equal. They're equivalent. You need to recognize that, okay? This is the last one I'm going to do for today. And then I'm going to shut up, and tomorrow is going to be a relatively quicker lesson as well. It's going to be a shorter video, and we're going to roll on from there, okay? So what are we going to do? There's a delta x. I have options here because I have a constant added to my delta x, and I can see the k is there. I can call this whole thing my c sub k if I wanted to. Remember, c sub k equals an x value. That's all it is. Which means this is going to be, because this means that symbol. And then if this whole thing's my c sub k, hey, there's my a. My width is 5, so I'm going to go up 5 from 2. Well, hey, that would put me at 7. Okay? Well, what's my function? Well, if this is my whole c sub x, this whole thing inside here is my function. So that's going to give me the square root of x. How do I denote my width? Delta x, we're just going to use differentials to show our change with our calculus notation is all it is. That's option numero uno. You know, there's my extent of my Spanish. It's not much. Okay. From here, I have option 2. I'm not even going to do it. I'm bad. So number 2, if I just said, hey, you now are my c sub k, well, if just this delta x is my c sub k, well, I'm not. I'm going to be starting at 0. Again, my width is 5, so now I'm just going to go to 5. My function, now just that is an x, okay? So that's going to be the square root of 2 plus x. Here's my width, or my delta x as a differential is there. And when you type both of these into your calculator, hopefully you do, you're going to find out what the sum is. That brings us to the end today. What was the whole point of today and the last few days? Okay? The whole point was teaching you, pestering the crap out of you, if I can say it, how the heck do we write this from the function? But on the AP test, they're not just going to show you this way. They're going to show you the limit of the sum, where you have to identify, ooh, write me as a definite integral. And if there's a constant added to your delta x to your c sub k value in there, because I can see delta x 5 over n, 5 over n, it's in there. Constant is added to that. Then I have 2 ways to do it, and I need to pick either. It doesn't matter which one I go. One of those answers would be below there. They could get really crafty on you, but they're not going to, okay? I could write a lot of these more, but my video would be 10 times too long. So that brings us to the end of today. Tomorrow we're going to look, whoa, that looks way different. Well, you're going to have to be able to write the definite integral from that as well and understand what and where and how it is, and we'll get there. That's tomorrow. Have a good day. Bye. Oh yeah, thanks for playing math again today.